welcome to BioLogic Science News. Today I bring you a story about findings from the Cassini spacecraft and what it means for the possibilities of alien life in the outer solar system. The entire Cassini mission is a titanic project, a culmination of the minds and labor of NASA and the European and Italian space agencies. It's a thing of beauty when you consider the original scope and compounding value of the Cassini mission to Saturn. On the NASA website, you can read about the Cassini's history and future vectors. Cassini has spent more than a decade orbiting Saturn, weaving throughout its many moons to gather data. You can follow the Cassini mission on NASA's website. At the time of recording, Cassini has just flown past Mimas, bringing back pictures of the moon's strangely large crater, Herschel. The crater gives the moon a creepy eyeball-like appearance, and Cassini's photos demonstrate that with an eerie clarity. Another moon of Saturn, the moon that's the subject of today's story, is the ice-covered world called Enceladus. The entire surface of the moon is coated in glaciers and ice sheets, and it's split by massive cracks that are visible from space. Cassini has generated huge volumes of data on Enceladus, on its ice sheets, its climate, its craters, and its massive splits, those cracks that carve up the planet's icy crust. On the ground, these cracks are like enormous valleys, like jagged mountainous sheets of ice were just snapped apart in miles-long sections. From space, they look like the tight folds of a blanket, or like a wound cut so deep that the scar can't even fill the space properly. The moon is a snowy white, and the scar tissue of the cracks is a bluish-gray or a light blue color. Cassini first detected liquid water in 2005, seeing it blast out of geysers and massive plumes from the surface of Enceladus. It was found that these plumes donate tiny particles of ice into the rings, which filter out into the outer E-ring beyond the orbital reaches of other moons like Mimas. In 2010, Cassini detected evidence of a liquid water ocean beneath the icy Enceladian crust. This is particularly exciting because a world-spanning ocean protected from radiation by kilometers of ice could be host to life. The tidal heating generated by gravitational interactions with its brother moons dumped energy into the subsurface oceans. With the source of energy, any potential life on Enceladus would have found a way to chemically exploit it. The question then becomes, is there enough heat to sustain life? Now, Cassini has given us new information about Enceladus that strengthens the case for life. The findings have been published in a journal called Nature Astronomy. In the article, the authors detail their methods and results. From an orbital height of 500 meters above the surface of Enceladus, they used microwave radiometry to scan a relatively thin, arcing region near the southern pole of the moon. I quote the study's abstract in describing massive icy cracks, or the sulci, in the South Pole ice sheets. The authors describe a warm subsurface region with prominent thermal anomalies that had not been identified before. These anomalies coincide with large fractures, similarly or structurally related to the sulci. The observations imply the presence of a broadly distributed heat production and transport system below the south polar terrain. The authors conclude that their findings indicate that only some kind of subsurface heat source can account for the anomalous findings. Mind you, the temperatures being talked about here are all very cold, between 70 and 90 degrees Kelvin. But when you're dealing with temperatures that low, any anomalous heat sources must be considered a possible source for life. After all, what is life if not a sophisticated collection of biomolecules, processing the available chemical energy of their environment to sustain themselves? So when I look at the data from the Cassini mission, and I see the anomalous heat energy that seems to be circulating in the subsurface oceans, I see a lot of potential for life. The so-called tiger stripe patterns of the cracks in the south pole of Enceladus look like vast panels of ice sealing in an ocean, with the turbulent waves beneath pummeling the ice from below, splintering it into three major pieces. Two expanses of fractured ice protrude outwards, like a pointing thumb and forefinger. Long, slender cracks, like massive wrinkles in the planet's skin, they cut deeply between these two expanses of exposed ice. Along these major cracks in the ice sheet, Cassini found its anomalous heat signatures. A larger heat map of the region reveals warmer temperatures at the heart of this icy complex, right where a subsurface ocean could be, with heat leaking out of the deep cracks that reach into the water. this anomalous heat found along the ice cracks, this subsurface heat source in the ice-covered oceans, all of this implies a warmer ocean than we previously thought. A warmer ocean is more hospitable to life. Consider the question I posed earlier. Is there enough heat to sustain life? If the tidal heating distorts Enceladus' core, but only provides a little bit of heat, there simply wouldn't be enough energy for the precursor biomolecules to form. It could be an empty, sterile ocean. But there could be enough heat to sustain biomolecules, and there could perhaps even be some kind of rudimentary cell. If there's enough heat, Enceladus' deep-sea thermal vents might host communities of single-celled organisms, just like they did on the primitive Earth. Its ocean floors might even be coated in rudimentary ecosystems of alien bacteria. If we take these findings into consideration, it becomes more feasible to conceive of an Enceladus with a more complex biological ecosystem. Who knows? One day, we might discover complex ecosystems of alien plants and alien fish swimming in Enceladus' oceans. Perhaps Cassini will be able to answer these questions before it sinks to its grave in the depths of Saturn.